Today we're going to use our vector valued functions, and we are going to talk about motion. Now, when we did motion last year in calculus, we only did it with linear motion. So we were either pacing back and forth, or we were moving up and down on a line. Okay? Now, the benefits to parametric equations, vector valued functions, is now we can move multi-directional and still be able to calculate velocity, acceleration, speed, etc. Okay? So let's talk about some things that we remember from rectilinear motion last year.
How do you pronounce that?
Rectilinear? You can just say linear. Linear motion. What do we remember about motion? Shout it out.
Nothing. Straight.
Okay? How do we get velocity?
Just as over time.
We kind of like derivative, absolute.
Okay? What else?
Acceleration is derivative of that. What's the derivative of acceleration? Isn't it derivative?
Sure. What else? What else did we calculate? How do we calculate distance versus displacement?
Integral and absolute value, and that one is.
Which one has the
Displacement has the absolute value.
No.
No.
Yeah.
Just can't.
Okay.
Why does it say note sheet?
Because I'm going to give you a note sheet. That's just my reminder.
Guided
so I
notes,
don't-
guided notes.
No. Anything else we want to try to remember?
When we do guided notes, we like write the entire sentence, but then take out a word that's supposed to be relevant and it's actually pointless. Because that's how
One time, dude.
we did it for stats once.
Once.
It was like last week or 2 weeks ago. But the word that was taken out is like it's so annoying.
Okay. So, Peter, we are looking at
Moving on.
we are looking at the notes document that is the second page of the velocity and acceleration worksheet. Okay, so here's everything you need to know about parametric vector valued functions. Okay, we obviously know that x prime is dx dt, y prime is dy dt. But you see that we have vectors. We have a position vector, a velocity vector, and an acceleration vector. So what we can do is to find each of those vectors, we have the position vector, we can take the derivatives of both of the components to get the velocity vector. Then we can take the derivative of both of the components to get the acceleration vector. Okay, so same rules apply, we're just talking about both components of the vector. Okay, dy dx is the rate of change of y with respect to x. Okay, we already know how to calculate dy dx and the second derivative with our parametric. Okay, we already know how to calculate speed. Okay, that's just the magnitude of our vector. Speed is the magnitude of our vector. So you can see we have the square root of dx dt squared plus dy dt squared. That's what we talked about even last week, right? That day I was gone and you did notes on your own. Okay. Distance traveled. We've already talked about arc length. Okay, it's just the integral of the speed. Okay, that has not changed. But distance traveled, I just want to remind you, is the antiderivative of the absolute value of the velocity. That's what we just talked about up here. Okay. You ready? Basically, it's everything that we did last year for motion, but now we have to think about two components at once. We're also going to take in what we worked with parametric equations, because that's what we're working with, parametric equations. We just have to apply it to this vector stuff that we have going on.
We haven't done this since last year.
I mean, we did it in here for you.
Since it's pretty recent.
Okay. A particle moves so that the position is given by x of t is t cubed plus 4t squared, and y of t is t to the fourth minus t cubed. Please write that set of parametric equations down.
40 squared.
What?
40 squared is
That's
that.
1600.
Business.
It takes this example just for you. I didn't. Okay, find the velocity vector at t is 1, the speed at t is 1, and the acceleration at t is 1. Okay, so if this is our position, then our velocity vector, chevrons because it's a vector, okay, the derivative of the horizontal component would be what?
3 squared plus 4.
8t? 80?
It's actually 0 because you already have 16 on
40 squared.
there. So
Okay, and the derivative of the vertical component?
That's 40 cubed. That's
Minus 3t squared. That's not quite as nice, is it?
4,000.
Okay.
6,000.
So our velocity vector at 1 would be
64,000.
11.1. Turkeys. I use the word turkeys for
Balance.
children who are being ornery.
yeah, we probably still have leftover turkey, so.
Or more like mischievous.
Who still has leftover turkey at their house?
I have leftover.
Yeah?
I mean, I don't think turkey.
I don't think
Yeah,
it's
there's only
Did you
two
not?
I think we did that turkey.
Okay, part B, calculate the speed. If I want the speed at t equals 1, what do we do with this vector?
Take the magnitude.
We find the magnitude.
Whoa.
Okay. Then we want the acceleration vector at t is 1. So the acceleration vector, we're just going to take the derivative of the velocity vector. Okay? The only thing that's different is we have vectors right now.
60 plus
60.
68.
60 plus 8. 12t squared minus 60. I know. This is terrible.
12 feet? That's 120.
So our acceleration vector at 1 would be 14. 6. Okay, we'll see if this works. I haven't gone to this website for a while. Okay, so fooplot.com, where we can do parametric equations. Okay. Help me out. It is t cubed plus 4t squared. Isn't this cool? And t to the fourth minus what?
You should probably figure out what the acceleration was at that time, so let's take it now.
What's the magnitude of acceleration?
Peter's like,
What's the magnitude of acceleration?
What is going on? Did I type it in wrong?
Peter was
Take the
correct.
magnitude of acceleration.
What?
Do you mean?
What's the magnitude of acceleration?
I'm gonna have to think about that one.
So wait a minute.
Is it jerk?
No, that's the derivative. We already talked about that.
Come on, you weirdo.
Okay, I don't know why it's not working. Sorry, guys.
It might be because you're putting it to a power.
Oh, you know what? It has to be S in this. I remember that.
You're kidding.
I know, isn't that ridiculous?
How the heck would you even know that?
It says this right.
Because it says S right here.
You have to say add.
No. There. That's what it looks like. So we go this way and then this way. Am I gonna have to take that away?
No.
That's good. I will tell you that on the AP Calculus BC test, there will be one free response question that is either parametric or what we do next semester, polar. One or the other. Okay, so let's look at another one. I really need to fix my projector. Peter, when you come back here, helping me with my projector. An object moving along a curve has the position x of t, y of t at time t with dx dt is t sine of t. Write it down. Dx dt is t sine of t. Dy dt is cosine of t squared. At time equals 2, the position is 1, 4.
According to somebody on Yahoo Answers, the magnitude of acceleration is the same as the magnitude of the velocity.
That is not even close to right, because 14 squared plus 6 squared would not be 122.
It's not.
You mean 140.
Okay. I appreciate you bringing humor to calculus.
They didn't need class teachers, did they? Their own business. That class them boring.
Okay. Find the acceleration vector for the particle at t is 2. Okay. Acceleration vector. Jake, what is our vertical, or excuse me, what's our horizontal component?
Did I say b theta?
Nope. A of t.
Oh, I think, sine of t plus t cosine t.
Great. Vertical component. Grayson.
Negative 2t sine t squared.
We want the acceleration at 2. Now, I will say this is a calculator question, and so if you are taking a derivative at a value and you have your calculator, would we have to go through that step? Technically, no. Okay, so we have, so make sure you are in radian mode, and I need the acceleration vector at 2. Okay, horizontal component. Vertical. Cool. Write an equation of the tangent line to the curve at t equals 2. What do we know about the coordinate at t equals 2? We know the coordinate's 1, 4. So what else do we need if we're going to write the equation of the tangent line? We need the slope. Okay, the slope. How do we get the slope? For a parametric, how do we get dy dx? Okay, that's good. We know dy dt is cosine of t squared, and we know dx dt is t sine of t. So we need this to be evaluated at t is 2. So you're using your calculators right now. Austin's using his calculator. Nick, do you have a question or are you squinting? Oh, did my pen like?
Yeah, but we have this
Oh, we better make sure it's.
Negative 0.359 is our slope, so there's the equation of our tangent line. Come on. Oh, stop, Grayson, stop. Peter could probably hear that in the recording.
I hope so. Let's
Tracy, what'd you do? Do it again.
No.
I can't do it again.
He like popped every single
I
like.
can do my knees.
I can do my wrist.
It's not a contest. It's not a contest.
Oh, that was a good
I'm
one.
gonna do
Can you hear it from there?
I can hear Sammy. Find the speed of the vector.
I needed to be that
Wait,
feels
one
so
second.
good
Can you
now.
go back?
Yeah.
That was a good one too. Go.
Why is it negative 1.3?
Sorry, I did this wrong and
When you plug 2 into this right here,
Yeah.
you should get it there.
You didn't take the derivative.
Oh, I did.
That's what I was going to do too, because you wrote that, and I'm like, are you taking?
Well, dy dx, this is dy dx evaluated.
Yeah, no, it just confused me because I'm like, didn't we get derivative graphs? And we're taking another derivative, but we're fine. I was like,
That's really not.
Sorry about that. Okay. Part C, find the speed of the vector. Speed means we do what?
We magnitude that thing.
We magnitude of the,
Derivative.
okay, of the velocity. So dx dt and dy dt. We already have those. So our speed is just the square root of dx dt squared plus dy dt squared.
Shouldn't that be?
That's what I wrote for.
I'm just asking questions.
Yeah. No one is Sometimes we have to say things out loud for us to realize.
Yeah, yeah, I agree. Let's optimize the box.
What's our speed?
Got 1.93.
Okay. The displacement of the particle. What do we have to do?
Displacement, that is the antiderivative not using an absolute value, which seems backwards.
Okay, so we need to do the antiderivative from 2 to 7. Now, we don't know how to actually take the antiderivative of cosine of t squared. We could use integration by parts for t sine of t, but guess what? We have our calculator in this example. So use your calculator, the Math 9 command, individually. Math 9 for the horizontal component, Math 9 for the vertical component. Cosine of t squared? Nope. Anybody have the horizontal component yet?
That's negative 6.36.
Awesome. 0.097, do you agree with that vertical component? Okay, so what does this mean? In the time, from the time t equals 2 to the time t equals 7, our particle has gone to the left 6.362 units and up 0.097 units. That's what's happening. Okay. Find the distance traveled. But what do we get to do for this one? We actually don't have to worry about that absolute value.
Which is the one where you multiply by 1. Is that like?
You just use this.
Okay, here we use the arc length formula for parametric. Okay, since these equations are defined parametrically, distance traveled, that's just arc length. Okay. Huh? Well, yes, if we were doing linear motion, we would have to figure out where it's positive versus negative and write them separately. But good news, we're doing parametrics, we can just do the arc length, which is a way easier calculation, right?
Yeah, so we don't just absolute value it.
No, we don't have to do that.
Could we? Could we not plug in the exact same thing? But we don't have to really-
Wait, so we're gonna get a number here. Just one number.
We get one number.
Instead of why is displacement?
Displacement is a vector because we are moving in 2 different directions. So we have to account for how far are we moving, how far are we displacing horizontally, and how far are we displacing vertically. Okay, so what's our distance traveled? 13? Point? Got you up?
Yep.
Okay, thank you. Sammy said hers was taking a long time too. You had like the, yep.
Starting years before me.
Okay, find a position at time t equals 1. Yours is still working? Nice. If we have to find a position, what does that mean we need to do? Okay, now you guys are saying anti-derived. Now we already talked about, can we take the antiderivative of cosine of t squared?
No.
No, we need the help of our calculator. So let's remember the fundamental theorem of calculus. The integral from 1 to 2 if we take the integral from 1 to 2 of our velocity vector, then we should get the position at 2 minus the position at 1. Do you agree?
Yeah.
Okay. Since we have to use our calculator to do the antiderivative of cosine of t squared, we're going to have to use the fundamental theorem of calculus. Otherwise, we can't find those c values to plug back in. Okay? Now, we know that the position at 2 is 1, 4. So now what you can do is you can take the integral from 1 to 2 of t sine of t. You can take the integral from 1 to 2 of cosine of t squared, and that will give us a position right here. Okay? So how about if you are sitting in pods 1 and 2, you find me the horizontal position. If you're sitting in pods 4 or 6, you're finding me the vertical position. As far as just from 1 to 2. So I guess the displacement is what I'm asking for.
Trying to find this of 1.
No, I'm just wanting for you to take the integral from 1 to 2 of the horizontal component. So the displacement of the horizontal.
1.44. 1.44. And negative 0.44.
What did you say this was?
1.44. Negative 0.44.
It doesn't matter if you put a T or a three.
Is this it?
Yeah.
Okay. So if we are looking for the position at 1,
Negative 0.44.
we would add this over, subtract this over, and our position at 1 is negative
0.440. And
4.44. And I did decide to make it just a coordinate because it's a position. If you made it a vector, that's fine too. It can be a position vector or a coordinate. Okay, does it feel like we learned anything new today?
yeah.
It does? Okay. Some of it is just like combining all the concepts to do it in a new way. Right? So we need some practice. Flip over your notes sheet. And you have a worksheet. That is your homework. You have 10 minutes left in class. I challenge you
To do 13?
to get through at least 1 and 2, if not 3. Huh? That's what. Okay.
Thick.
Why are you saying thick?
I don't know.
It's one piece of paper.